Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. We humans pride ourselves on our rich, colorful world. We see roughly 10 million different shades, thanks to the 3 types of cone cells in our eyes. But imagine a dimension of light that is entirely invisible to you. Not ultraviolet, not infrared, but the very orientation of the light wave itself. This unseen dimension is polarization, and for the tiny, often transparent, inhabitants of the deep sea, it is the key to survival. To understand polarization, picture light not as a simple ray, but as a wave vibrating perpendicular to its direction of travel. Normal sunlight is unpolarized, meaning the vibrations occur on every possible plane. But once light bounces off a reflective surface, or, crucially, when it passes through a medium like water, the vibrations become restricted, vibrating predominantly on a single plane. That is polarized light. Humans can perceive the effects of polarization only indirectly. Think of polarized sunglasses reducing glare. But our biological detectors, the photoreceptors in our retinas, are symmetrical and average out the light, effectively masking the polarization signal. We are blind to this fundamental property of the light around us. Yet, hundreds of feet below the ocean's surface, where the sun's reach is a faint, ethereal blue, specialized crustaceans have evolved the capacity to read this signal like an open book. The deep ocean is an environment defined by physics. As sunlight penetrates the water, it is scattered by molecules and particulates. This scattering process inherently polarizes the light. In the upper zones, the light is polarized horizontally. Deeper down, the remaining blue light follows predictable polarization patterns relative to the sun's position, even when the sun itself is long gone from view. For creatures like deep-sea amphipods and copepods, this predictable pattern of polarized light acts as a giant, internal navigation system, a biological compass. How do they achieve this feat? It comes down to the architecture of their photoreceptors. Unlike our symmetrical rods and cones, these crustaceans possess specialized structures called microvilli. These tiny, finger-like projections are densely packed with light-sensitive pigments, but critically, they are arranged orthogonally, in precise rows, often crisscrossing at 90-degree angles. This highly ordered structure means that light vibrating on one plane will be absorbed differently than light vibrating on another. By comparing the absorption rates across adjacent, differently oriented microvilli, the crustacean brain can map out the polarization landscape. This polarization sensing capability offers immense advantages in the perpetual twilight of their habitat. The first, as mentioned, is navigation. Since the polarization pattern of downwelling light is fixed relative to the solar or lunar azimuth, these animals can maintain a constant bearing, enabling long-distance migrations or efficient return trips to feeding grounds, all without relying on celestial bodies they cannot directly see. The second major advantage is camouflage detection. Many deep-sea organisms have evolved transparency as their ultimate defensive strategy. However, even perfectly transparent tissues can alter the polarization of light passing through them, an effect known as birefringence. To a human eye, a jellyfish is invisible. To a crustacean with polarization vision, the jellyfish glows subtly as the outline of its muscle fibers and internal organs refracts the polarized background light. Transparency is immediately broken. Finally, polarization is used for communication. Researchers have found that some benthic crustaceans can actively manipulate their own structural coloration, the patterns on their shells, to produce highly polarized signals. These signals are invisible to most predators, but brilliant to conspecifics. This allows for intimate, secret communication. A polarized language used for courtship rituals, species recognition, or threat displays that bypasses the sensory capabilities of their enemies. This incredible biological adaptation is not just a fascinating quirk of nature, it is a blueprint for technological innovation. Engineers are actively studying these crustacean eyes to design next-generation optical devices. Imagine advanced underwater cameras that can see through murky water, medical imaging tools that detect subtle structural changes in tissue invisible to current scans, or satellite sensors that measure atmospheric pollution with unprecedented sensitivity. The deep-sea crustacean, living in darkness, shows us how to see light in a dimension we have barely begun to explore. For more incredible facts like this, don't forget to subscribe and turn on notifications.